All right, so this is an introduction to solving absolute value inequalities, and I want to start this with real-life problems. Real-life problems, we've learned how to work with absolute value equations, and an application of an absolute value equation or an absolute value expression is the absolute value deviation, which is referred to, it's the absolute deviation of a number from a given value is the absolute value of the difference of x and the given value. So notice it is just an absolute value. It's the same as what we've been working with. We have x minus some given number. So let's explore this a little bit more. So again, the absolute value deviation of a number x from a given value is the absolute value of the difference of x and the given value. So we could just replace absolute value instead of absolute deviation. The deviation, remember, that means like something that deviates away from the norm. And you've probably heard the expression of measuring something, and the measurement might be accurate to plus or minus 0.05 centimeters. So plus or minus means a deviation away from the norm. Okay, so if we have the absolute value of x minus 3 equals 5, and that means the distance from some number x and 3 is equal to 5. So the distance is 5. So absolute value is that distance away. So absolute deviation means the same thing, that 5 is the absolute deviation from 3. And so on the number line, 3 is that center point, and we have our deviation to the left, minus 5 would be negative 2, and to the right would be positive 8, so plus and minus 5. So in a real-world example, to see how this applies, let's say you're buying a new computer, and the table shows the prices of computers in a store advertisement. You're willing to pay the mean price with an absolute deviation of at most $100. How many of the computer prices would meet your condition? So we're going to let X represent the price that you're willing to pay. And so obviously there's more than one price that you're willing to pay if the deviation is at most 100. And that's the deviation from the mean price. So let's understand what this problem is saying. We know the price of 10 computers as shown in the table, and you're asked to find how many computers are at most from $100 from the mean price. Well, let's make a plan. What do you need to know first? Well, we need to know the mean price of the computers that are listed, because it says we want a deviation of at most $100 from the mean price. So we have to find the mean. So remember that mean is the same as average. So to find the average of all the prices, we add all of them up together, and there are 10 prices shown in the table. So the sum of all of those prices is $6,640, and divide by 10, and we get $664 as the mean price. So we're going to set up and look for the prices that are within $100 of 664, either give or take, either less than one minus 100 or more plus 100. So you could probably look at this table of values and figure them out just by looking at the table, if we understand what this means. Our mean value is 664, and we're willing to purchase a computer, and probably based on what features it has, but between $100 less than 664 and $100 more than 664. So let's use the equation for an absolute deviation, which is absolute value, and the mean price to write an absolute value equation with a deviation of $100. So this is what that absolute value equation would look like. That we want X as the computer price we're willing to pay, and the difference between that price and 664 could be 100. All right, so now we want to consider the condition. We said you're willing to pay an absolute deviation of at most $100. So what does that mean, at most? That means no more than $100 greater than 664 or less than 664. So our center point, if we think about graphing this equation, we have 664 as the mean price. That's our center point. And then We want to find the extreme boundary points or values that we would consider as our price. So that means we want to think about $100 less than 664, which is 564, or $100 more, which is 764. So now we're going to rewrite the absolute value equation that we had on the previous slide as an inequality to represent at most. So if we think about what at most means, it can't be more than 100, so it's less than or equal to. So our absolute value of x minus 664 must be less than or equal to $100. So let's graph the solution again and indicate by shading the inequality that represents the computer prices that meet our condition. So here's our graph with our center point and our $100 less and $100 more. And then we want to shade in between because we're going to consider any price that's in between the left boundary and the right boundary. So the shading indicates all possible prices in between. And so now let's think about solving this absolute value inequality. We're going to write it as a compound inequality. And since our shading is in between the boundary points, then that means we're going to use that and inequality, where x minus 664, the quantity inside the absolute value, is in between the negative 100 and the positive 100, because our center point is 664. If you see in the graph, and you can go 100 less or 100 more. So we take the expression in the absolute value bar, and we write the compound inequality saying that we're going to solve this considering going 100 less or consider going 100 more. So now let's solve it like we reviewed solving compound inequalities. I need to solve for x. So we would add 664 to the middle and to the left and to the right. And so we would get negative 100 plus 664 is 564, which these are the boundary points that we had already found. And 764 is the right boundary point that we already found. And then we'll use our answer, our graph, to answer the question in the problem. How many of the computer prices meet your condition in less than below? So we'd have to go back to the table, but the prices that would meet our condition are these. These are 6 prices that would meet the condition. Okay, so now we'll talk about what your assignment is and look at the topic page.